Welcome to Calculus. Today we will investigate how to find particular solutions by initial conditions and separation of variables. We'll take a look at three differential equations. Our first example is the differential equation dy dx equals e to the power of x over y squared. And our initial conditions given as y at 1 equals the cube root of 3e plus 1. We'll start out by separating the variables. So again, what that entails is moving everything that involves y to one side. We'll move it to the left, and also moving everything that involves x to the other side, to the right side. So our initial separation is going to look something like this. I'm going to move the y squared by multiplication. I'll cancel it there on the right. And so on the left side, I'm going to get y squared dy. And I'm also going to move the dx, since that involves x, to the right side. So that's going to equal e to the power of x dx. And with those just two kind of multiplications, cancellations, we have separated our variables. Everything with y is on the left, everything with x is on the right. So at that point, what I want to do is I want to integrate. So I'm going to apply the integration to the left side and to the right side. And we'll integrate as usual. So the integration of y squared dy is going to be 1/3 y cubed. Then we'll integrate the right side. The integration of e to the x dx is going to be simply e to the x. And we'll also include our plus c. So that's a good general solution. What we're interested in, however, is the particular solution when y at 1 equals the cube root of 3e plus 1. Essentially, I want to plug in an x and a y value so that I can solve for c, take that c, substitute it back in, and that'll give us a particular solution. So let's do that. So I see that my y value is going to be given by this right side, the cube root of 3e plus 1. So I'm going to plug that in. So that'll be 1/3 times the cube root of 3e plus 1 cubed equals e. Now I got to pick up my x value. My x value is this 1 in the initial condition. So it's going to be e to the power of 1 plus c. So at that point, I've substituted an x value and a y value from the initial conditions. I want to simplify and solve for c. So I see that I've got a cube of a cube root. So those are inverse operations. They'll cancel out. So then I've got 1/3 times 3e plus 1 there on the left. So that's going to be e plus 1/3. And the right side's pretty much as it is, e plus c. So with a simple subtraction of e from both sides, we get the value of c is equal to 1/3. So we're ready to create our particular solution. I'm going to pick up our general solution there, which again is 1/3 y cubed equals e to the x plus c. And at this point, I'm going to plug in the c values so that our solution becomes particular. So that'll be 1/3 y cubed equals e to the x plus 1/3. And that's a good particular solution. I do want to solve that for y so that I can have an explicit equation here where y equals something in terms of x. So to do so, I just have two steps. Basically, need to multiply by 3 to cancel the third. And then I want to take the cube root of y cubed. And so making those two changes, we'll end up with this explicit particular solution. Y equals the cube root of 3e to the power of x. And if I distribute that 3 times 1/3, we get plus 1. And that is our final answer there. Y equals the cube root of 3x plus 1. Our second example involves e to the power of x as well. In fact, e to the power of 2y. But the arrangement's a little different. So again, what we'll begin with is a separation of variables. So it's really the same type of multiplication to cancel, and then it'll show up on the other side. So over here on the left, I'm going to multiply by dx to cancel dx, and it'll lodge there with 2x. Then on the right side, I'm going to multiply by e to the power of 2y to cancel that denominator value, and that's going to lodge over on the left. So we'll get this separated equation, e to the power of 2y dy equals 2x dx. Again, I'm ready to integrate once I've separated my variables. So there on the left side, e to the power of 2y, if I think about its antiderivative, I know that e to the power of a variable is itself, is its own derivative. So I need to think of how I need to treat this. Really, it's a composed function, e to the power of 2y. If I use the chain rule, that's going to differentiate as e to the 2e to the power of 2y. So I need to cancel that 2 by multiplying by a half. So our antiderivative e to the power of 2y is going to be 1/2 e to the power of 2y. And then on the left side here, we've got that coefficient 2. And then if I integrate x, that's going to be 1/2 x to the power of 2 plus c. And I see that I've got a cancellation. 2 times half is going to cancel. So I've got a good general solution there. I'll just rewrite it very quickly so that I don't have that cancellation present. So 1/2 e to the power of 2y equals x squared plus c. So now I'm ready to pick up my initial conditions and plug in so that I can solve for c. So the y value here for the initial condition is natural log of 5 over 2. So we'll plug that in. We've got 1/2 e to the power of 2 times that natural log of 5 over 2. And we'll also plug in the x value from the initial condition, which is given as -1. So that's going to be -1 squared plus c. So at that point, I've got everything in terms of either a constant or c. So I want to solve for c. I've got a cancellation in my power here. 2 divided by 2 will cancel. And then I see that what's left is e to the power of natural log of 5. So that's really inverse operations. E as an exponential, and natural log is log base e. The net result of all that is just going to be that exponent 5. So this is going to reduce down to 1/2 times 5. And then -1 squared is going to be +1 plus c. On the left here, we're going to have 5 over 2. And if I subtract 1 over as 2 over 2, I see that the value of c is 3/2. So now once I've got c, just like with our previous example, I'm ready to write our particular solution. So let's take that and plug in our new value for c, 3/2. So again, let me record the general solution here. It's 1/2 e to the power of 2y equals x squared plus c. And now we'll plug in our c value. Here's our particular solution. 1/2 e to the power of 2y equals x squared plus 3 over 2. As with our first example, I do want to solve for y. I want an explicit equation for y equals something in terms of x. So I'm going to start that final step here by multiplying by 2 both sides. And that's going to give me e to the power of 2y equals 2x squared plus 3. When I distribute that 2 on the right. And then to get y out of the power, I'm going to apply natural logarithm to both sides. And what that'll do, according to my exponent rules, it's going to bring the 2y out front, and the natural log of e is 1. So all that's going to cancel. All that we'll have left is 2y equals natural log 2x squared plus 3. And then to finally solve for y, we'll divide by 2 or equivalently multiply by half. And we'll get y equals 1/2 times the natural log of 2x squared plus 3. And that is our explicit particular solution for this differential equation with those initial conditions. Our final example is a trigonometric differential equation. It's also given in the prime notation instead of Leibniz. So I'm seeing here I got y prime equals 1 over secant squared of y. Initial conditions y at -2 equals 0. Remember, when you have Leibniz or prime notation, you can convert it to Leibniz dy dx, since that's really works well with separation of variables. So I'll just convert it there. Equals 1 over secant squared of y. So as I move my terms around to separate the variables, I'll cancel the dx. It'll lodge there with the 1. I'll also cancel secant squared y here on the right, and it'll lodge by dy. So our differential equation at this point is going to look like secant squared y dy equals 1 dx, or just dx. And with that, I've got my variables separated. The y's are on the left, the x's are on the right. I'll integrate. So now just thinking about a antiderivative for secant squared y dy, that's going to be our tangent. So the left side is going to integrate as tangent of y. Right side is just really, you can think of it as a 1. If I integrate 1, that's just x plus c. So we're good to go now in terms of having a general solution. We want to get our particular solution now by solving for c. Again, I'll take my initial conditions, substitute in the y and the x, solve for c. So we'll have tangent of initial condition when x is -2, y is 0. So tangent of 0 equals -2 plus c. Again, that -2 is the x value of my initial condition. So we're ready to solve for c. So I'm thinking on the unit circle, I got to evaluate tangent at 0. So that's that unique triangle. It's very much a flat triangle where my x or horizontal value is 1, my y value is 0. So it's a triangle with 0 height. So remember, tangent is y over x. So it's going to be 0 over 1, which is just 0. So that's 0 equals -2 plus c. If I add 2 over, I solve for c. c equals 2. So with that, I'm ready to convert my general solution to a particular solution. Let's pull the general one. It's tangent y equals x plus c. Let's substitute in our c value of 2. So tangent of y equals x plus 2. And the only thing that's left, as with our first two examples, at that point, I need to solve for y. So to cancel the tangent function, I want to take the inverse tangent of both sides. That'll cancel. So on the left now, all I've got is y. And on the right side, I apply that inverse tangent function. And that completes my explicit particular solution. Y equals inverse tangent of x plus 2. And that completes that third example that involves trigonometric functions. Well, thank you for joining for these 3 examples of finding particular solutions of differential equations from initial conditions and separation of variables. See you soon.